Let's look at this de Broglie wavelength idea again. We know that the wavelength of a particle is Planck's constant divided by the momentum. But if I draw a wave with a nice constant wavelength, well then it goes on forever. A wave with a single wavelength is just a sine function that goes on forever. In other words, there is no well-defined position for this wave. Now I can add up several waves with slightly different wavelengths in a Fourier series, and I can get a wave packet that builds up and then comes back down. In this case, I've got a fairly well-defined position, not perfectly well-defined, but within a narrow range. But the trade-off I get is that I had to add up many different wavelengths to confine this to a single space. In other words, now I've got more than one wavelength, so more than one momentum. I've got a smaller uncertainty in position, but in return for having a larger uncertainty in momentum. Now I can make this wave packet smaller. I can make it really as narrow as I like. But again, the trade-off is that if I make this wave packet narrower, I have to use more different wavelengths, and as a result, more different momenta. I get a bigger change in momentum. This was recognized by Heisenberg, who came up with a very important principle called the Heisenberg Uncertainty Principle. What it says is that our uncertainty in position times our uncertainty in momentum is always greater than or equal to Planck's constant divided by 2 pi. This is called h bar. It's simply Planck's constant over 2 pi. Sometimes you'll see this with a Planck's constant, or an h bar over 2. Depends on how we define uncertainty in the x direction and uncertainty in the p direction, or uncertainty in momentum. Notice it's the uncertainty in x combined with the momentum in that same direction. The uncertainty in the y direction compared with the y direction momentum. Uncertainty in z with the z direction momentum. This is a fundamental principle of physics. There are certain things that we cannot measure with arbitrary accuracy. Position and momentum, for example. If I measured position completely accurately, I would know nothing about the momentum. If I had the momentum with complete accuracy, I would know nothing about the position. Sometimes it's phrased as an experiment problem. Namely, that if I localize a particle to a single point, then I've totally messed up its momentum. Whereas if I measure the position and time as a particle goes through 2 gates, well, now I have to have a difference in position, introducing uncertainty in the position. However, it's much deeper than that. As we showed, if we're going to think of the particles as waves, then to make it into a small wave packet, we have to use many different wavelengths, which means many different momenta. It's an intrinsic property of the particle. It doesn't have both a well-defined position and a well-defined momentum. I should point out, however, that Planck's constant over 2 pi, h bar, is a tremendously small number. For large macroscopic things, the uncertainty in position and the uncertainty in momentum can be tremendously small and still be much greater than h bar. So this really doesn't put any limits on how accurately we can measure how fast a car goes or how fast a ball flies through the air. It only becomes a problem when we're dealing with accurate measurements at the atomic scale.